All right. So we're going to start talking about graphs. So here's a cubic or a quartic. Where are any minimums or maximums? Okay, so where is there a minimum?
There's a local minimum that's x equals 0. There's the it's called global minimum.
Absolute, actually. All right, so I kind of have a point here, right? Those would be the minimums, right? So this one's known as a local min, and that one's known as an absolute min. Okay. Any dip is going to be a local. If it's the lowest point on the possible graph, that's what makes it the absolute. Do I have any maximums on this graph? Yeah, right here. So that would be a local max. Do we have an absolute maximum in this graph? No, because these keep going. Okay. In pre-calc or algebra 2 or college algebra, which you probably found minimums and maximums, but they were for quadratics. Or if you found it for anything else, you're basically estimating where they were using a graphing calculator to find it. So today we're going to start using calculus to be able to find them. All right, here's just a few quick definitions. Absolute maximum minimum is the value of f in the domain where every single value is either greater than it or lower than it, depending on maximum or minimum. A local maximum or minimum is when the value of f is always going to be below. So f of c is greater than f of x when that x is close to it. So either on either side of it. So basically you're getting up to that peak. Same thing with the minimum. These are pretty self-explanatory. You do not need to know the exact notation that's right here, yes?
Just by curiosity, can a absolute minimum or absolute max also be a local max?
Yes. Yeah. So you can classify them all as local, and then the absolute value is basically like a step above it. It's like a square to it's like a square to a rectangle. All squares are rectangles, but not all of them are squares. Same concept. The extreme value theorem states if you are looking on a closed interval, so if the actual graph is stopping at specific points. So for example, on this one, if I said they were ending here, so it ended there and didn't keep going, that right there would be an absolute max. So if you have a closed interval, the endpoints also have to be looked at in terms of local mins and maxes, or absolute mins and maxes. So in that case, that would be an absolute maximum. You don't typically qualify the extremes as locals. They're just the absolutes. So I wouldn't mark that one as a local maximum, for example. All right. Any questions with that? Yes. If they were exactly the same, yes. Back here. what, let me actually take away those because those two don't really work for this. Now, thinking about what we've learned over the past month and a half plus, what do all three of those points have in common? You yet, because I know you know the answer. What do all three of those points have in common? Yeah. Okay. Okay, you can go now.
The derivatives are equal to 0.
Why?
Because just like what you said, as it's going either if it's minimum, it's going less and less down, and then it changes to going up, but between that equals the derivative of 0.
Okay. So derivatives tell me slope, right? Right. That's the key. That tangent line is going to be 0 at that point, right? The slope of that tangent line at those points would be 0. So, Mr. Fermat, another famous mathematician, stated that if f has a local minimum or maximum at that c, then the derivative at that, and if the derivative exists, then the derivative equals 0. So if it has a local minimum or maximum, and the derivative exists, then the derivative has to equal 0. Okay. All right. Find me the derivative of this function. All right. What's the derivative? Good. So here's my graph. So let's factor the derivative and find my zeros. Because based on Fermat's theorem, right, those 2 points should be 0. So 0 equals 3x squared minus 6x minus 9. Those two should be zeros. So how do I factor this?
Factor out the 3.
Yeah, they're all divisible by 3. Get rid of that first. It makes your life a lot easier. And actually, the reason there's no 3 there is because then I can divide by the 3 and it disappears. Okay? Two numbers are multiplied to -3 and add to -2. Okay, which means x equals 3 and -1. So my absolute mins and or my local mins and maxes here are zeros in my derivative. Make sense? All right. Find me where my local mins and maxes are for this problem. What's the derivative?
Bm's to the 2.
Okay. So what's x equal? Yeah.
That with their minimum.
Well, let's see. There's my graph. If I graph x to the third, that's what it looks like, right? What's at 0? Is that a local minimum or maximum? Is it? Yes or no?
So
Okay. By definition, what does a local min or max have to have? Everything either has to be lower than that point around it or higher than that point around it, right? At that point, is the stuff on the left and the right either both higher or both lower than that point? No. The left is lower, the right is higher, right? Okay. So what we figured out is that just because the derivative is 0 does not mean it is going to be a local min or max. It can be. It doesn't have to be. So the converse of Fermat's law or Fermat's theorem isn't true. So if we have the derivative, that does not necessarily mean it is a local minimum or maximum. Okay. What's the derivative of this? No.
it's 1 and negative 1. And nothing at 0.
Right. Remember that the absolute value function, the derivative is actually a piecewise function because absolute value, you have to look at both two different directions, right? So this problem is really the negative x when x is less than 0 and x when x is greater than 0, greater than or equal to 0. So the derivative of that is -1 when x is less than 0 and 1 when x is greater than 0. And it does not exist when x equals 0. So, but what's the graph look like for an absolute value function? Okay, so is there a local min or max?
By the definition. Surrounding.
That's the absolute value function, right? Okay. Did the definition of an absolute minimum or maximum state anything about a derivative? So let's go back and look at that.
Guys, theorem did.
Fermat's theorem did. So there's the definition of a minimum or a maximum, right? Is there anything about derivatives in there? No. So that absolute value function definitely has an absolute minimum at that point. So let's look at Fermat's theorem and see, does that violate what Fermat's theorem says? It says if f has a local minimum or maximum and if the derivative exists, then it has to be zero. So because it says and the derivative exists, that means this theorem doesn't work for the absolute value because the derivative doesn't exist. However, that does mean that if a derivative doesn't exist, we could possibly have a minimum or maximum there. We're going to have to look at those points. All right, so what we've figured out is what's known as critical numbers. So a critical number is a number that is in the domain of f such that either the derivative equals zero or the derivative does not equal zero. Or sorry, does not exist. That does not equal zero. Does not exist. So it is where the derivative doesn't exist or the derivative equals zero. Those are going to be our critical numbers. And then those numbers we would go in and test to determine if they are going to be a local min, local max, or possibly nothing, as we saw in the x to the third part. Oops, where is, oh, I closed that page. Darn it. All right, so find me the critical numbers for this problem. All right, what's the derivative of this?
It's minus 243 over x root of what? Wait,
That's x, that's right. Yep. Or all right. So set it equal to 0. How am I solving it?
add the proportion on both sides. So it goes. And then you multiply both sides by x squared.
And then I do what?
And then you take the positive fifth root.
Fifth root can only be positive. Well, fifth root will be, because it's odd, it'll be whatever the sign is. All right, so I got x equals 3. Okay. Are there any other critical numbers?
This makes this for the function of limits that x equals 0.
Does the function not exist at x equals 0, or does the derivative not exist at x equals 0? All right, so there's two parts to this. So that is, and then does not exist at x equals 0. So when you're looking for your critical numbers, you're finding where the derivative equals 0 and where the derivative does not exist. The second part of that critical number thing is very important, though. That number has to be in the domain of the original function. So you have to check your critical numbers to make sure they are in the domain of the original function. Is x equals 3 in the domain of the original function? If I plug 3 into that, will that work?
Yeah.
Okay. You don't have to find the number. You just have to say, you just have to figure out, can it work or not work? So in this case, yes, x equals 3 works. Does x equals 0 work in the original problem? No, because I have I've divided by x to the third. So my critical number for this one is x equals 3 only.
X equals 0 doesn't work because you have b divided.
0.
That would just mean that it's not in the domain of the equation.
Correct. That means it's not in the domain of my original function. So since it's not in the domain of my original function, it can't be a minimum, a local minimum, or a local maximum because it doesn't exist.
So if that was any other number other than 0, then it would be?
Yes, that's the x equals 3 does.
Right.
Okay, so yeah, so there is a possibility that a number that does not exist in the domain or does not exist for the derivative can work in the original problem. If that makes sense.
Yeah.
And it might in the next problem I'm going to do. So. Find my derivative. Yeah, the whole concept of finding derivatives isn't going away. You're going to do this constantly. What do we got to do for this one? Yeah, we got to do the quotient for this one. I'm going to move the negative sign up to the top. So on the last test, I really wasn't forcing the simplification, which is fine because we really weren't using anything after that point. However, now we need to use it. We need to do something more with this. So you are going to have to simplify some things. However, you want to simplify based on what you need. So for a derivative like this, what are the two things that I'm looking for the critical numbers? I'm looking for what two things?
When the derivative is equal to zero,
When
it doesn't exist.
Right. Okay. Well, so when it's zero and when it doesn't exist. So in a quotient, what does that mean? When is the quotient equal to zero? Right. So I don't really care about the bottom when it equals zero. All I'm looking at is the top. So 0 equals the top. So now, while I'm rewriting this, distribute things and let's see if we can clean this up a little. So I've got 12x to the fourth plus or minus 1/4 x squared plus minus 8x to the fourth. So this is where algebra skills really come into play, especially in this part here, making sure that you can factor those two things, and then remembering that that's the difference of two squares. It will make your life a lot easier when you're factoring things. So this now equals x equals 0, 1/4, and negative 1/4. So far we've got three critical numbers. What's next? We still need one more thing for the derivative.
Find where the derivative doesn't exist.
Right, I need to know where the derivative doesn't exist, right? Now, however, and this is where, again, understanding what's going on and figuring things out, where the denominator doesn't equal 0 for the derivative, where that piece or each of those pieces has to also be in the domain of the original function, right? What do you notice about the denominator of this derivative and the denominator of the original function?
They have the same factor.
They have the same factor, right? They're basically the same. The only difference is the denominator and the derivative is squared. So, and what's the first thing I'm going to get rid of when I'm setting it equal to 0 anyway is the square. So in essence, the derivative of the denominator of the derivative, when that doesn't exist, the function doesn't exist either. So you can save yourself some work if you remember and look for those types of things. If not, you set the bottom equal to 0, solve for the number, and plug them back in. Okay. But that one, so I'm not going to go through and do an extra step there. However, we do have to make sure these exist in the original function. So if I plug 0 into the denominator, does that exist? Does it work? Yeah, because that'd be 1/12, right? Yes. Because there was a negative in front of the whole fraction. So I just put it up top. Instead of just putting it out in the front of the whole thing and then remembering I have to move it through. No problem. Okay, so 0 I know works. If I plug in 1/4, so the only way this is not going to work is this has got to be 1/12, right? Because it's got to be negative 1/12 plus 1/12 to get 0. If I plug in 1/4, is that going to make it different? No. So I have three critical numbers. Those are my three critical numbers. All right. Next one. I'll rewrite it so it's a little larger. Okay, if I'm in my derivative. So one of the things about how you did with in pre-calculus or college algebra, stuff like that, they were all pretty much polynomials. Okay. However, not every function is going to be that. So we still need to be able to find the absolute minimums and maximums for any type of function. Okay, because when you're modeling things, they're not always going to be nice polynomial functions. So, and the rules for absolute minimums and maximums didn't say, oh, it's got to only be x to the whatever power. How do I do this? How do I do the derivative of this problem? What do I got to do? I do have to do the chain rule, but what's the overreaching part is the product rule. So I got to split it up first. So f prime is going to be almost, except for the -4. That's where you have to use your chain rule. So, and that one actually is just 1.
Yeah, that's fine.
Yeah. So as you get further and further, and as you get better at doing this, you will start to recognize little things like this and just do the chain rule automatically. That's just practice. And the same thing actually with the next one, where we have x plus 1 times not to the 9th. We know that's 9x plus 1 to the 8th, and the derivative inside is just 1, so I don't have to worry about that extra piece. That's practice. That's literally just repetition and doing them over. The more you do it, the better you're going to get at those things. All right, so my derivative is -4 e to the -4x times x plus 1 to the 9th plus e to the -4x times 9 x plus 1 to the 8th. Now comes every piece of algebra skill that you've ever had. Because we have to set this equal to 0 and solve it. So whenever you have a problem that's really, really messy, like this one, look and see if you can pull things out. So what's the same here and here? So I have e to the -4x is the same in both of them.
So 1 plus 9.
No. Okay. Before we get into that, is there anything else I can take out? Yeah. I have x plus 1 to the 9th in the first one, x plus 1 to the 8th in the second one. Let's pull that out. Now, what do I have left? Well, I have -4 here, and then x plus 1. And actually, I took all that out, so that's just plus 1.
It'd be 9.
Oh, you're right, it is 9. There is a 9 there. Sorry. Thank you. I missed the 9. All right. Does that answer solve the problem that you were talking about before, a second ago that I couldn't catch?
No, I don't get this. No.
Okay, so we're looking at things that we can take out. So that and that are the same. Because we're looking at each box as a term. So I've got that, and then I have x plus 1 here and an x plus 1 here. I have 9 of them here and 8 of them here. So I pull out the most, which is the 8. that's what became that thing there. Yes, no? Okay, and then whatever's left, which in this case is the -4 and one of those x plus 1s, and then the 9 that I forgot over here. This is why I said, this is like, I've been saying all along, the mistakes you're going to make are not calculus mistakes. They're algebra mistakes. Like, I'm pretty sure most of you could figure out the derivative on the top. You're going to make all the mistakes. But the thing is, when you're making the calculus mistakes, it's because you're just like, you're still learning that, which is fine. The algebra mistakes, once you start getting the calculus, you're still going to make those algebra mistakes. Even my Calc 2 class, that's literally the mistakes they make, is all algebra based. So, and that's like problems like this. It's like, okay, I got to solve it for 0. Like forgetting, I can pull things out. I can make my life a little bit easier. All right, so let's clean this part up a little bit, and then I can look at each of the pieces and set each piece equal to 0. So -4x plus 5. Yeah. Now it's all a multiplication, right? Set each piece equal to 0. Can that happen? No. There's nothing I can raise e to the power to get 0. That's where the asymptote is. So that gives me nothing. This one, x is -1. And this one, x is 5/4. All right. What's the last thing I need to do? Yes. Well, this one actually has 2 more steps. I have to verify that those are actually in the original function first. So I have x equals -1 and x equals 5/4. So if I plug those in, do both those work? Yeah, the domain of E is all real numbers. The domain of a polynomial is all real numbers. So those are both going to work. Okay, the second part of this problem is it wants us to find the absolute minimums and absolute maximums. Okay. So when it's asking for those, we are going to take these numbers here that we just got. It's asking for just the absolutes. It is not asking for locals. Right? So you are going to plug those 4 numbers into the original problem and see which one is the highest and which one is the lowest.
With algebra, can use the calculator.
So you can use the calculator. However, notice it says right here, give exact answers, not decimal ones. So if you were to plug this into the calculator because of the E and everything else, odds are you're going to get a decimal. So let's look at each of these numbers. I know it sounds like it sucks. And I'm not going to lie, it's not that fun. Notice I didn't go through and do all the work. Which one's the minimum? That's the min. Still is negative. Now, these two, one of those is going to be the max, one's not. Now's where I throw it in a calculator and get it as a decimal just to see what it comes out to be. E to the negative fifth. Now I throw them in there. And that first one's going to be the maximum. And just so you know, you can literally type it like that into Desmos. I mean, not into Desmos, into the into Alex. You don't have to simplify it any more than that. It shouldn't, as long as your parentheses and stuff are in the right spot. That's like 2 times 4 and 4 times 2, same thing. It's as long as you don't mess up anything else in there. So I have it in front. It doesn't matter. Let's do one. All right, how many people did not catch that sine x was a chain rule? Sine squared x is the same as sine x squared, which means we have to do the chain rule for it. So you get 2 sine x, and the derivative of sine x is cosine x, minus 5 sine x. So next, set it equal to 0. Remember, when just as it might sound crazy because we typically were dealing with polynomials, However, the reason we factored polynomials is that multiplication makes it easy to find zeros, because 0 times anything is going to give you 0. So just because this is not a polynomial per se, doesn't mean factoring is not going to be the easiest way to get things set equal to 0. So same process in this one. You do not want to move the 5 sine x over to the other side and divide, because you're going to lose information. So factor, get it set up as multiplication. So this way we can set each piece equal to 0 and solve it that way. So we've got 5 sine x equals 0. So sine x equals 0. And 2 cosine x minus 1 equals 0. So cosine x equals 1/2. I don't have x yet, though. Now, this problem gave us a domain. It says between pi over 4 and pi over 2. So the question is where does these work on that, in that domain? So where is sine of x 0 between pi over 4 and pi over 2? That's 0 at 0 and pi. So you're right, it's not. So that one gives us no zeros. Where is cosine of x 1/2? Right, pi over 3. Any questions with that? This is where that remembering of the unit circle is going to help. All right, so next thing for this one is we need to figure out our absolute min and absolute max. So I've got 3 numbers to plug in. I've got those 3 numbers I'm plugging in to see which ones work. What's sine of pi over 4? That's 5/6.
Square root 2/2.
Square root of 2/2. Oh wait, which does come out to be 1/2 when you square it. And then cosine is also square root of 2/2. All right, do pi/3 and pi/2. So max, min. Questions? Honestly, the thing about it is, so there's two main things. You have to remember to find the derivative. So that's step one. And then you have to be able to do the algebra and plug the stuff back in. Those are the basic things. So, all right. there's two theorems here. So Rolle's theorem says that these three things have to be true for this to work. F is continuous on an interval. You can find the derivative of that, and that f of A equals f of B. If those three things exist, then there's some number C in between A and B where the derivative has to be 0. Actually, what? I'm going to put this on a different slide. I want to give you a picture of this. So basically what he's saying is, as long as at some point, so those 2 points have to be exactly the same. Okay? Then at some point in time, between those 2 points, there has to be a minimum or a maximum, basically. There has to be a place where my derivative is going to be 0. Now, if you think logically about this, it makes sense. If I have 2 points that are exactly the same, at some point, it's got to turn to get back there, right? It's the only way it gets back to that point, is it's got to turn. Now, it can turn multiple times, like we did here, or it can turn anyway. Like, it doesn't make much difference. One little catch at the bottom. There you go. So that's what Rolle's theorem stated. Now, we look at Gauss and goes, yeah, that makes sense. He was the one that actually originally said it. Nobody had thought of it before he did. So that's why he got his name on things. All right. These 3 things have to be true for this to work, though. If they are not, it does not work. The mean value theorem, which is actually way more important, is just an expansion of that. So the mean value theorem says that, actually, this picture. If f is continuous and f is differentiable, so those two still have to be true. The difference is that A doesn't have to be equal B. What it says is that there is a number C such that the slopes are going to be the same. So, like this right here, here's my, that's that slope. At some point over here, the slopes have to be equal to that. Same thing on this one. There's got to be another, there's got to be a point between those two where I have an identical slope. So at some point, so this is a story, and I don't know how true it is, but it totally makes sense for this problem. So back in the day when the Massachusetts had toll booths on the Mass Pike, So if you ever drove back on the Mass Bike where they had toll booths, it sucked. You had to literally like go through and pay money at the points. Now they just charge you electronically. You don't realize you're paying, but you're still paying. So you would get a ticket, and that ticket would have a time on it. And then you go to the next toll booth and you give it to them, and they would normally they would tell you how much you paid because it would know where you got on and where you got off. Well, there was a time on that ticket. They also knew exactly the time between the two toll booths, like the distance between them. So they could figure out, okay, you shouldn't be able to make it in any more time than this, any shorter time than this, unless you were not doing the speed limit. Okay? So if you had driven 10 miles, or let's say you drove an hour, we'll make this easy. You drove 1 hour, so 60 minutes, and the speed limit was 65 miles an hour. You should only be able to do 65 miles in that 1 hour. You could be speeding at some point in it, but you have to slow down to get to that 65 miles. So if you did 75 miles in that 1 hour, you obviously were speeding. That's what this says. That's what the mean value theorem basically allows us to do. It's saying it's taking the average of these 2 points, and at some point between those two, you had to be doing the exact same average. Okay? That's the mean value theorem. So the story went that my father had a friend who literally went between toll booth and toll booth, and as soon as he went through the second toll booth, the cop pulled him over for doing 100 miles an hour. And he argued, how you never caught me on camera thing. He goes, and he pulled out the ticket. He says, yes, but I know you were speeding. And in essence, that's what this rule allows. Okay, so the mean value theorem says you take the average, and at some point between it, the average has to be the same, which in this case is going to be my slope formula and my derivative. All right. The topic in ALEKS, which is what I'm going to go over now, is slightly weird for this question. No, not weird in a bad way, actually. Weird in a good way. Because it doesn't ask you to apply it. It just asks you, can you apply it? So it's going to give you a graph like this. And what it's asking is, can you do Rolle's theorem? And it goes, okay, so between 6 and 8. So if we look at the graph, between 6 and 8, there's 3 things that it has to meet, right? Between 6 and 8, it has to be, what are the 3 things for Rolle's theorem? It has to be continuous, differentiable, and for Rolle's, they have to be the same. Okay? So, is it continuous between 6 and 8? No. So therefore, it does not satisfy it. And it does not satisfy it because it is not continuous and it is not differentiable. 6 and 8 do actually equal each other, so that does meet. Okay? So if it was a closed circle, it would exist at that point. If it's an open circle, it doesn't. So if that was closed, it still wouldn't be continuous because there's a break in it. If 6 was open, it still wouldn't be continuous at 6. If I had gone from 1 to 4 and 6 didn't work, it wouldn't have mattered at that point. So this one does not satisfy Rolle's theorem because it is not continuous, and since it's not continuous, it is not differentiable. All right, now they want you to do the mean value theorem from 0 to 6. So from 0 to 6. So we're looking at and you can draw on this, which is nice. 0 to 6. Is it, so the 2 things for the mean value theorem is continuous and differentiable. Is it continuous between 0 and 6? Is it differentiable between 0 and 6? Yes. It does not have to equal each other. So, yes to both those. So, it does satisfy the mean value theorem. All it wants you to do now is estimate where the slope is going to be about the same as that. So maybe 3.5. Or maybe like right there. Maybe. Maybe closer to 3. Let's try 3. It does say estimate, so I'm going to suspect it's going to give you a range in it. Okay. There, let's try another one of these. All right. Between 3 and 6. Does Rolle's theorem work? I don't know. I'm going to go with probably does. So they're the same. Is it continuous? Yeah. Is it differentiable? Not differentiable right there. It's a corner. Remember, there's the way when you're looking at differentiable, it's not differentiable when it's broken or at a corner where it drastically changes direction. In that case, it's going from that way to that way really quickly. There's not a nice curve to it. So in this case, it doesn't. And it's because it is not differentiable on those two. If it was differentiable, let's say that curve wasn't there. Actually, I think that would have probably been where the answer was, is at 5. All right, from 6 to 10. From 6 to 10. Is it continuous? Differentiable? Yes. So then there's got to be a value that works. Eight? Sound about right? Yeah. Want to do one more? Are we good? All right, let's do one more. Oh, good. One for Rolle's rule that might actually work. All right. Rolle's theorem 4 to 8. They're equal. Is it continuous? Is it differentiable? Yep. So it does work. So do we have so 7 or 5? I'm going to see if you don't have to put them both. Because the way the question words, it just says give the estimate. 5 would work and 7 would work. I'm going to put 1 just to see if it wants both or not. Mean value theorem from 0 to 4. From 0 to 4. Continuous? Differentiable? No. Not differentiable at 2. So it is not, and it's because it is not differentiable. Now, this one's tricky because technically f of 0 does not equal f of 4. Is that a criteria of the mean value theorem? No. So that answer should not be true. All right, so good news. You only have to put 1 of the answers there. And they didn't screw that piece up. All right. Chapter 4 is open, so start working on chapter 4's topics. And I will see you on Thursday.
Thank you.
You're welcome.